Hello, and thanks for joining. My name is Erwin Knippenberg. I'm a young professional and economist in the World Bank Poverty Practice. And for the Data for Policy 2021 International Conference, I'm presenting the following paper, a geospatial analysis of displacement in Afghanistan using nighttime lights data, submission 61. This paper was co-authored by Anais, Dahmani, Walker Cosmidu Bradley, Johanna Belanger, and myself, all at the World Bank. The key takeaways of this paper is that the objective of the work was to test whether geospatial data can provide a proxy for displacement flows in conflict-affected countries. We leverage a case study in northwestern Afghanistan and show that nightlights data can capture the influx of people displaced by drought into existing settlements, and that this effect is concave, meaning that for smaller settlements, we have a stronger correlation between the inflow of people and the increase in nightlights. When using these results for predictive purposes, the model can accurately predict settlements with a net inflow of people about 2/3 of the time. Given the constraints of accessibility on the ground in conflict-affected countries and the widespread availability of high-resolution geospatial data that is also updated quite frequently, this demonstrates the feasibility of using such data at scale to infer displacement patterns and inform humanitarian operations. First, a note about the relevance given current and recent events. As of August 15, 2021, the Taliban have seized Kabul. The escalating conflict and drought has exacerbated displacement. Humanitarian agencies and the United Nations have sought to maintain and expand their presence on the ground and have provided a continued commitment to provide emergency assistance. The agency's limited footprint on the ground highlights the importance of alternative remote monitoring mechanisms to identify displacement patterns in order to best target assistance and facilitate the very important work that they do. In terms of the broader context, Afghanistan is in the top 5 globally in terms of internally displaced people due to both conflict and natural disasters. It has a high level of internal displacement, and it ranks first with the highest number of IDPs due to natural disaster, most notably drought. As of August 2021, a total of 5 million people out of a population of 32 million, so almost 1 in 6, were internally displaced. This displacement is driven by a combination of conflict and drought, and as you can see here, is concentrated in the west, around Herat and Badghis, in the southwest, and then in the center, around Kabul and Nangarhar. Where this fits in the broader literature is a contribution to the work produced by the Humanitarian Development Nexus to predict displacement flows using variations in satellite imagery-derived data. Quinn et al. Showed that machine learning algorithms can return precise estimates of forcibly displaced people and geographic structures using remotely sensed data. Our study directly complements existing humanitarian work using nightlights data in particular. Lee and Lee explored the spatial and temporal patterns of nighttime lights in Syria and found that there was a moderate correlation between the loss of nightlights and people being displaced in each province. Now, this was at a much higher level of aggregation than we are proposing, where we are looking down at the settlement level. Our study builds on recent progress made to assess displacement through geospatial proxy indicators, including both urban and natural measures. The Global Report on Internal Displacement from the Internal Displacement Monitoring Center contributed to the global research on displacement using indicators of housing destruction and flooding gathered through satellite and aerial imagery. So there is a wealth of data out there and a wealth of efforts to show how this data can be used to monitor displacement in near real time. In this particular instance, we are studying the 2018 drought and displacement, which until the drought now in 2021 was one of the most severe droughts to affect Afghanistan. The effects of the drought were concentrated in the west and northwest, and were driven by record low levels of precipitation, a deficit of 70% relative to normal levels. This also meant a reduced snowpack, which in Afghanistan, because the snow in the spring then melts and the runoff feeds irrigation, has led to desiccation of fields and crops failing. These adverse impacts have translated into large displacement flows. Out of the current IDPs located in the country, it is estimated about 300,000 individuals arrived in Herat in 2018, and more than 160,000 arrived in Badghis at the same time. Given the security situation and economic opportunities in urban areas, many of these displaced peoples remained in urban settlements rather than returning to their home, thereby contributing to the growth of these settlements, which would then be reflected in nighttime lights data. So here's an illustration of how we can see these settlements visually on maps. Looking at a before and after the drought imagery, we see clear evidence of settlement camps in the outskirts of Kalaina, which is the provincial capital of Badghis. We then worked with our colleagues at the International Organization for Migration, IOM, and they shared with us a unique set of data, the Displacement Tracking Matrix, which identifies detailed displacement patterns in Afghanistan, and specifically in the Badghis region, before and during the 2018 drought. The IOM data being used for this analysis corresponds to 10 rounds of data that were collected through the baseline mobility assessment conducted between January 2018 and December 2020. This information is collected through a series of key informants where focus groups are held at the settlement level. It includes information on the settlement's location using GIS coordinates and inflows and outflows of displaced populations, as well as certain control variables which we use that, such as settlement size, types of employment in the settlement, and so forth. This displacement tracking matrix is a detailed and unique source of information on displacement patterns in Afghanistan and a unique type of administrative data. Here on the left, you'll see in blue are all the settlement dots with a 1 kilometer buffer, which allows us to extract the nightlights. And then you see them overlaid with estimated existing settlements. So many of these people moved into existing settlements or on the outskirts of larger settlements such as Kalaina. Here's a snapshot of the geospatial data that we used. Nighttime lights data is a sort of data that is increasingly popular among both development practitioners and economists in general. It is, simply put, the level of luminosity that is exhibited at night by any sort of economic activity, be it streetlights, be it houses, being highways, and is considered to be a very strong correlation both of economic activity and of population levels. And you can see here in the corner, we have clear evidence of Kalaina being a bright spot of nightlights. So what we wanted to see is, over this 2-year period, how have the nightlights changed and whether that change correlates with the inflow of displaced people, which we know based on this settlement data from IOM. So we extracted, using a 1 kilometer buffer, the nightlights data for each of these settlements, and then we overlaid it with the displacement data. In terms of our results, we ran 2 specifications. First, a linear analysis of nightlights against previous nightlights interacted with total inflow to see whether total inflow is indeed correlated with the level of nightlights, and then a nonlinear analysis to infer any sort of nonlinearity in the correlation. We found that the linear regression suggests that existing settlements have a higher net inflow of displaced population between 2018 and 2020. These settlements have a larger average growth in nightlights. So this validates the primary hypothesis of the paper, that population inflows can therefore be captured using nightlights trend data. In addition, using the nonlinear regression analysis, this suggests that the effect is concave. Concretely, what this means is that the relationship between the growth, the change in nightlights, and the population inflow is largest for the smallest settlements. Now, this makes sense intuitively because the smallest settlements are where a large inflow of people would be most visible and would most likely reflect in an expansion of the settlement that would then be captured geospatially. This method can therefore better capture displacements to secondary cities and towns, which would nicely complement traditional data collection efforts, which are often concentrated in larger cities because that's where the bulk of people move to, but not necessarily where all of displaced people move to. In terms of robustness checks, we want to address any endogeneity concerns and concerns that initial conditions may act as confounding variables. Notably, because nightlights reflect population levels and economic activity, are people simply moving to the places with the highest level of economic growth? We found that the results are robust when controlling for the initial settlement size as well as for the job composition within the settlement, the proportion of people who are working in agriculture versus non-agriculture, which is an indicator of the level of economic sophistication of the settlement. We found no correlation between pre-drought level of nightlights, which is the baseline level of population and economic activity, and the level of either inflows or outflows of displaced people, which suggests that truly we are capturing, when we see an increase in nightlights, the effect of these inflows and outflows. Finally, we sought to predict whether or not we can use this correlation to determine which settlements are actually seeing a net inflow of people and therefore should be prioritized when it comes to sending in humanitarian aid and assistance. We found that when distinguishing between areas with a net outflow and net inflow, we were able to predict net inflow with a 66% accuracy rate. This prediction outperforms a random iteration model where we simply look at if we were just guessing how accurate this would be. However, this model can still be further refined using more powerful algorithms, using different sources of geospatial data, such as building footprints, and perhaps even looking at adjacent pixels. However, this validates the premise that you can actually, at a quite high level of precision, predict the inflow of displaced people using remote sensing data. And with that, I'd like to thank you all for watching this presentation. Again, my name is Erwin Knippenberg at the World Bank. Thank you to my co-authors who worked with me on this. And please do feel free to reach out with any questions or comments. Thank you again.